Hello and welcome to Alkenes 5. So the theme of this lesson is that it sort of further explores the electrophilic addition mechanism, but specifically with reference to what we call asymmetrical or unsymmetrical alkenes. I'll explain what that means a little bit after the starter questions. It also looks at the relative stabilities of carbocations. That's a word we've already seen, but we haven't really done any comparison in terms of stability, and that's something that we need to do in this lesson. It's going to be a long one, possibly 2 sittings really, because of all the additional explanation, but it's going to be in one video. Right then, let's have a look at some starter questions. So there they are. Pause the video and have a go at these on scrap paper or a whiteboard. Up to you whether you use your notes or not, right? I would recommend starting without notes, and then if you need them, consulting them. So pause the video and provide some answers. Okay, so here's what we should have. Displayed formula of sulfuric acid, the name of the compound formed, and the definition of molecular formula. So it's only a short one, no name and outline for this bit. We've got plenty of that to come. Right then, let's have a little think about what asymmetry looks like in alkenes. I'm going to use a very simple model to explain this rather than drawing the alkenes, because again, we're going to get plenty of practice doing that as we look at the specific examples. So the blue section on the left there is supposed to represent asymmetrical alkene. So a good example of this is ethene. Obviously, there are hydrogen atoms in an alkene like that. I've not drawn those because really I'm just focusing on what happens at the double bond. So let's say we do an addition reaction. There should really be a bond here. And we add a hydrogen halide like hydrogen bromide across the double bond, right? Then bonds are formed between the separate atoms in the hydrogen halide and the carbon atoms. And we've looked at the mechanism to explain how that works. Like I said, this is a very simplistic model, but there is a reason for that. Okay, so the first thing to point out is it makes no difference which atom the yellow blob is attached to and which one the red blob is attached to. Because if we take our model of ethene and we draw it the other way around, we have not created something, oh, hold on. We've not created something new. All we've done is horizontally inverted. We've swapped it on the horizontal axis, right? That will be the same molecule. The same argument applies if we kind of turn the hydrogen halide around over here and we say we're adding it in the opposite kind of orientation. It makes no difference to the product, right? This has to do with the fact that ethene is a very much a symmetrical alkene. And this also works wherever you've got a double bond right in the middle of a molecule. So for example, in the case of butene, it would be a similar sort of argument, okay? But, right, we're going to look at the specifics very soon, right? Before we do though, let's just kind of extend this slightly. Let's say for the sake of argument that our alkene has 3 atoms and it only contains 1 double bond. And so now the double bond kind of has a location. It's not just the center of the molecule, it's between carbon 1 and carbon 2, right? So this would be propene, which in fact is going to be the first example we start with. Okay, so I'm not going to redraw the entirety of the model, right? But let's just think about it a little bit. What we're going to get in an addition reaction here is the double bond will have been broken. We understand that that's how addition reactions work. Even before we looked at the mechanism, we'd kind of looked at this idea. So there's going to now be 3 carbons which are single bonded to one another. However, right, if we think about adding the same kind of electrophile, let's say it's, I don't know, hydrogen bromide or whatever, okay? The position we attach that yellow or that red circle now actually matters, right? Because now you can't just assume that you're going to get exactly the same structure. Let's see what I mean, right? We've put the yellow circle in the 1 position and the red circle in the 2 position, okay? If we were to redraw our product with 3 carbon atoms joined by single bonds, and then attach the yellow circle in the 2 position and the red circle in the 1 position, that is not the same molecule. It is a position isomer of the first molecule. Okay? Now, the point that we're trying to make here is that actually, when you've got an asymmetrical alkene, such as propene, right, the carbon atoms that your reagent of addition gets attached to, it actually makes a difference to the outcome of the reaction, right? It makes a difference to the identity of your product. And there's a little bit of a rabbit hole we have to go down that explains why you might get one more than the other, whether it's a mixture, all this kind of stuff, okay? So that's what we're going to do. Let's put the model to one side and start looking at some real molecules, okay? So we're going to use a very similar example here, but using carbon atoms now. Here's propene, which is an asymmetrical alkene, and hydrogen chloride, okay? So looking at this, you should be able to pause the video and draw on 2 curly arrows, right? Because you should understand how this works. We also need some partial charge on our hydrogen halide, and then you can stop because we need to talk about what's going to happen next. Okay, so what you should be doing is marking on a delta plus on the hydrogen, a delta minus on the chlorine. Remember that that relationship just exists because of the difference in electronegativity between hydrogen and chlorine. We then have 2 curly arrows showing electron pair movements, formation of a carbon-hydrogen bond, and the movement of the bonding pair of electrons in the HCl bond onto the Cl to form a chloride ion. Okay, and the next thing for us to do is to draw the intermediate, the carbocation. However, because propene is asymmetrical, we basically have a divergent pathway. There's 2 ways this can now go, right? This first step of the mechanism doesn't suggest one way or the other, but there is now 2 ways it can go. So let's have a look at what those 2 ways are. Okay, we have 2 examples here. In the first example, just use a little bit of highlighting to help, right? What we're saying is this hydrogen, you don't need to highlight that, I'm just using it to kind of make a point, is now attached to this carbon, right? So the double bond was between the carbon in the middle and the carbon on the right. That's now been broken, and there's now a hydrogen atom attached to that middle carbon, and there's a positive charge on the carbon on the right-hand side, okay? In example 2, in the second pathway, that hydrogen atom instead has been added here. Now, because of the carefully sort of selected examples I've used up until this point, this hasn't been an issue because we've always been looking at ethene or, for example, butene, where it doesn't matter which order we do it in. But this time it does, because this divergent pathway is going to result in 2 different products, position isomers of one another. So let's complete the mech anyway, right? You need a curly arrow on both versions of this. You wouldn't normally draw both versions, and I'll explain why afterwards. But for now, when we're explaining it, 2 curly arrows, 1 on the left-hand side scheme and 1 on the right-hand side scheme. So what we should have is formation of a CCl bond, okay? In both cases, it's just that the carbon of interest is in a different position, the one with the positive charge on it, okay? So those are our carbocation intermediates, and they're different, and that's a key part of what we're sort of exploring now. Right, then let's finish up this kind of pathway, or each pathway, by showing that actually what this results in is position isomers of 1 chloropropane and 2 chloropropane. So as necessary, you can pause the video and make your notes. So the question we have to answer is, which pathway is favored? Is it one or the other? Is it both? How does this work, right? Because obviously in this scenario, we don't necessarily know to begin with what the product or products is going to be, okay? So, right, the facts are this reaction produces a mixture. So the short version is you actually get both of these position isomers. You get 1 chloropropane and 2 chloropropane. Okay. However, the key thing is that they are not produced in equal quantities. So it's not like a 50-50 mixture. It's not like 1 molecule of 1 chloropropane is produced for every 1 molecule of 2 chloropropane. It's not an equal probability of making each of these things, right? We say that 2-chloropropane is the major product. And that's a key bit of terminology used in this topic. What it means is you get a lot more of that product. So that's what major product means. I don't want to put specific numbers on it, but let's just say for the sake of argument, 90% of what's formed is this isomer, 2-chloropropane, and 10% of what's formed is 1-chloropropane. I don't know what the actual proportions are because it's going to vary by reaction, but let's just say for the sake of argument, right? 90% of one and 10% of the other. So it is a mixture, but it can be a very unequal mixture. I'm sure that you can figure out that that means we classify 1-chloropropane as the minor product. Chemistry is often a science of opposites. Okay, and that's true here in terms of this terminology. Again, what that means is you get a lot less of that isomer. Now, to explain this, there's quite a lot for us to discuss still, but we're going to go back up into this kind of divergent, scheme with the 2 reaction pathways and do a little bit of further annotation. Make sure you've paused the video and made your notes as appropriate. Right then. So the mechanism is done, that's all fine, right? What we'll do is add a little bit of information here. So I've numbered the big arrows here, and that's basically referring to the idea of there being 2 pathways for the reaction, okay? So we called one of them pathway 1, the one on the left, and the other one pathway 2. The numbers don't really mean anything, it's just to discriminate between them, right? So pathway 1 on the left here, the one that makes 1-chloropropane, right? This occurs more slowly. So this pathway has a lower rate of reaction, okay? Again, science of opposites. Pathway 2 has a higher rate of reaction comparatively, okay? The reaction overall could still be quite slow or could quite quick, but we're comparing basically these 2 pathways. It's like a fork in the road, and going one way is quicker than the other. So the higher rate occurs in pathway 2, right? And that kind of explains why you get more of that isomer. If you imagine you run your reaction for 10 minutes or whatever, right? In that 10 minutes, because pathway 2 is quicker, more molecules of 2-chloropropane are formed, and so you end up with more of them in the product mixture. So again, we can kind of annotate a little bit there. Pathway 1 is slower, pathway 2 is quicker. That's the kind of plain English version of what we've just been discussing. Okay? So, right, the other thing that we need to talk about, just tidy this up a little bit, is that this explanation has to do with the nature of the carbocation that's formed. Okay? We haven't really looked at carbocation classification, but we have done, or you should have done a little bit on classification of perhaps halogenoalkanes. Okay? So in organic chemistry, a lot of the time, we classify things as primary, secondary, or tertiary. And that pretty much always has to do with the number of carbon atoms attached to another carbon atom. This is hard to explain in words, right? So what we're really getting at is the carbon atom that has the positive charge in a carbocation is classified according to the number of carbon atoms that are attached to that carbon atom. So if I just stick with kind of the highlighting a little bit, the blue one is the one we're classifying, and the yellow represents the number of carbon atoms attached to that. So we can see there's a difference, right? When there is one carbon atom attached to the C+ in a carbocation, we classify it as a primary carbocation. Again, this is the same kind of idea as classifying halogenoalkanes or later on alcohols. Okay, and it has to do with the number of carbon atoms attached. So in brackets, one carbon attached to C+. That's what we're getting at, right? The yellow one is the one that's attached to C+, and there's only one of them. Again, you can probably guess and see the pattern about what's coming on the right-hand side. When there are two carbon atoms attached to the positively charged carbon in the carbocation, we classify it as a secondary carbocation. And that's because there are two carbons attached to the C+. So that's the difference, right? The classification of the carbocation. We're still not there with the explanation, but we're getting there, okay? There are also tertiary carbocations. We'll have a little look at an example of those very, very soon, okay? I should also point out that there's kind of another rule we use to describe this sometimes, but it's not required for AQA A-level. It's called Markovnikov's rule. If you are interested or if you see anything written about that, it's basically a different way of looking at the same thing that we're doing now. But I'm not going to mention it in any depth. It's just in case you're doing a bit of reading around and you see it. Not required for AQA A-level. Right then, so let's have a look at the difference between carbocations. Again, we're going to come back to this a little bit. So carbocations have different stabilities, all right? And there's a little explanation we give for this as well. But the rank order here is we put tertiary carbocations at the top and primary ones at the bottom. So you might need to pause the video and make your notes. Then we'll talk about this a little further. Okay, so a tertiary carbocation, as you might expect, is one that has 3 carbons attached to the C+. And there's an example of that down in the bottom left. I've used the signifier R because R is what we use for sort of generic alkyl groups. So R could be CH3, a methyl group, or it could be a longer part of a hydrocarbon chain, right? The point is that it could be something that's quite variable. Hopefully you get the idea though, right? The primary and the secondary, again, very similar to what we've just looked at, but there's an R instead of CH3s or CH2s. So, right, what we've got here is a comparison of stability. And this links to something we talked about 5 minutes ago, right? So let's just pop back up to this reaction scheme. We'll be done with it soon. We said that reaction 1 had a lower rate and reaction 2 had a higher rate. This has to do with the relative stabilities of the carbocation intermediates. Reaction 1 occurs via a primary carbocation. Primary carbocations are less stable. Reaction 2 occurs via a secondary carbocation intermediate, and secondary carbocations are more stable comparatively. Because the intermediate in pathway 2 is more stable, pathway 2 has a higher rate. That intermediate is kind of more likely to be formed, okay? And that's as much kind of detail as we need to give. The phrasing we use here is that we'd say, and I'm not going to do this for both examples, but we'd say pathway 2 has a higher rate of reaction. It occurs via a secondary carbocation, which is more stable. That's the language we tend to use, okay? And you could obviously give the corresponding statement for pathway 1. I'm not going to bother, but you'd say it occurs via a primary carbocation, which is less stable, right? I'm not going to write it down, but you'd say something along those lines. That's as much kind of info you generally need to give, right? For explaining why, for example, 2-chloropropane is the major product of this reaction. So that's a lot of new interconnected ideas. There's one more bit to add before we do a little bit of practice writing out these statements and identifying major and minor products and drawing mechanisms, right? And it has to do with giving a little explanation about why there's this difference in stability. Okay? So pause the video as appropriate and make your notes, and we'll have a look at that in a sec. Okay, so remember that there was this kind of rank order, right? The last thing we kind of have to do with this before we can do a little bit of practice is just to give some justification for the sort of difference in stability. This isn't a major part of this topic, but it is something you're supposed to be familiar with, and it kind of rears its head again in year 13, or a similar concept rears its head again in year 13 in a different topic. So there's a phrase we use to describe why tertiary carbocations are more stable than secondary ones and so on. And it's called the positive inductive effect. Now, put simply, this can be kind of thought of as an electron pushing, all right? So alkyl groups have what we call a positive inductive effect. And essentially what we're saying is that if you have methyl or ethyl or propyl groups nearby to another atom, it's possible that they can push electron density towards that other atom. This has an impact when you have carbocations, right? So let's start with the primary one and think about that. In the primary carbocation, if we use a kind of blue chevron, if you like, to get our heads around that, we could say that the neighboring alkyl group pushes electron density towards that positively charged carbon. Again, we're simplifying a little bit, but the reason that might happen is it stabilizes the positive charge on that carbon. Having a positive charge or a negative charge on something is kind of a site of instability, right? Because it's a kind of formal or, whole positive charge, right? And that's part of the reason why this is an intermediate and continues to react, right? It forms a new bond so that that charge goes away, all right? In the primary case, you get the positive inductive effect from one neighboring alkyl group. In the secondary carbocation, you get that positive inductive effect from two neighboring alkyl groups. So the secondary carbocation has more electron density being pushed towards that positive charge and is stabilized more. So that's why the secondary carbocation is more stable comparatively. Finally, if you have a tertiary carbocation, then what you have is a positive inductive effect from three different directions, right? And therefore even more stability. So it might seem like an unsatisfactory kind of explanation. It's as much as we really need, right? And there are probably problems with it. I'm probably simplifying, in terms of what's actually happening. But this is the way we tend to view it at A level. So just learn the phrase positive inductive effect. Using the model that I've just kind of described with the blue chevrons, you can hopefully see that in the tertiary carbocation, there is a greater positive inductive effect, which makes it more stable. That's as much as you'd probably need to say. One more thing about this, another good way of viewing this is, to do with the fact that if you localize the charge, right? So let's say we've got, a carbocation with 4 carbon atoms. If you put the plus on the end, it's kind of just there isolated on its own on the end. And you can probably sort of get the sense that that's going to be less stable than if we put it in the middle of the molecule, because you're not spreading the charge around as much in the left-hand model. This is another way of thinking about it, right? If you've got a very localized, strong, isolated positive charge, it's going to be less stable. Again, if we make an isomer of that, and then we put our plus slap bang in the middle, that's the most kind of spread around, okay? Again, that's not a very technical way of viewing it, but it's just yet another way of examining it. So I don't want to make a big deal about this section. I want to focus mainly on identifying major and minor products and learning the language of more stable, less stable. And so I'm just going to get rid of that bit for now. Right then. here's a task, guided initially, because the second part is going to be a bit less guided. Okay, you need to think about methyl propene and hydrogen bromide. Okay, so this is a branched alkene. So start by drawing the displayed formula of that molecule. Then, using the same logic we've just done, try and figure out how you're going to draw the structure of the major and minor products of this reaction. Then name and outline the mechanism to form the major product only, right? So we only need one mech, the one that forms the major products. That tends to be how the exam questions work. They don't usually want the mechanism for the minor product. And then finally give an explanation in terms of relative stability of carbocations, why this is the major product. Okay, so you might find this tricky, but that's all right. Take your time, look at your notes from the previous bit and make sure you get the structure of methyl propene correct to begin with, and you should be okay. Okay, so I'm assuming that you've had a go at this question now. If you haven't, you need to pause the video and do so. If you've had a go but got a bit stuck, that's okay, I understand. You know, we're going to talk through it now anyway. Okay. So here's the DF of methyl propene. Doesn't matter if your double bond's on the left or the right, could even be pointing upwards technically. The position of it doesn't actually matter as long as relatively you've got the correct number of carbons and hydrogens. Okay. So, right, assuming that we're sticking with my structure, we could either add our hydrogen here, or our bromine there, the bromide ion, or we could do it in reverse order, right? That's the outcome we've got. And if you've actually thought about it for long enough, you'll realize that the major product is the one where the bromine ends up on position 2, and the minor product is the one where the bromine ends up in position 1. Okay, this is using exactly the same logic that we used in that first worked example. It might be that you found it hard to get to this stage without perhaps drawing the mechanism. If you needed to do that to work it out initially, I understand, that's fine. So now that we know what the major product is, it's electrophilic addition. So this follows the same pattern that it always follows. We've got a polar hydrogen halide and 2 curly arrows that do exactly the same thing that they always do. And remember that this first step of the mech doesn't give you any information about which carbon the hydrogen is going to be attached to, right? You'd show that in the next section. So there we go. We'd have one more curly arrow there to show the formation of the carbon-bromine bond in position 2. And we would have this molecule, which I guess we would call 2-bromo-methyl-propane, because the double bond's gone now. So 2-bromo-methyl-propane. I don't think I asked for it to be named, but that's what you'd call it. So, not got the answer here. Let's explain this, right? This pathway occurs via a tertiary carbocation, right? Your carbon atom here, with the positive charge on it, actually has 3 carbons attached to it. So if you cross-reference that with the list that we did, right, then you'd see that, okay? So that's a tertiary carbocation. This is more stable than the primary carbocation that forms the minor product. Okay, I'm not going to draw that initially, but we'll just scan back upwards and look at the minor products, and we'll talk about where the positive charge would be. Okay, so your minor product was this, where the bromine was in the 1 position. Remember, This is where the positive charge would have been in the middle of the mechanism, which we haven't drawn, and there's one carbon attached to that. So that would be a primary carbocation that it occurs by. Okay? Hopefully you're okay with that. If you're still kind of feeling a little bit unsure, the practice will help. And if you need to use your notes quite a bit to try and get through it, then that's absolutely fine. Okay? But what we now need to do is a little more independent practice. And this will be the last part of the lesson, right? So here's the task. So for each of these examples, what you need to do is outline the mechanism to form the major product. You don't need to name it because it's always going to be electrophilic addition. But outline the mechanism to form the major products and do a quick comparison of the possible carbocations. So again, in terms of relative stability, you can draw them both and look at them if you want. But there are 4 examples. As usual, the one that's in red is a bit more tricky, right? It's not impossible, but it's if you can't do that, then don't worry, right, basically. But have a go at 1 to 3 at least. And as usual, once you've done that, you pause the video and had a go at them, then we can have a look at the solutions and finish up. Okay, so there's not going to be all the writing that we need necessarily on these, but let's have a look. Butanene and hydrogen iodide, sorry. It's going to look like this. There's your first step. Forming the major product, it's going to occur via a secondary carbocation rather than a primary, which is what you'd get on the end, because this is more stable, remember. And there's our major product. The minor products would have occurred via that carbocation, which is less stable. So if I went a bit quick, you might just need to go back and pause at various frames, but hopefully you get the idea. For number 2, this time we've got 2-methyl pent-2ene, okay, hydrogen chloride. So here's the mech. It's definitely going to go this way, right? Because you've got a tertiary carbocation that can, form the major product, which will look like that. 2-chloro, 2-methyl pentane. Then your minor products would have been formed via this, which is actually a secondary carbocation, which is comparatively less stable. Again, you don't need to draw the minor product. I just want you to think about the carbocation that would be formed. Although you could draw it, you just stick a chlorine attached to that carbon that's got the plus. So for number 3, same sort of format, ramping the difficulty a little bit because it involves sulfuric acid, but you use exactly the same logic here with your negative ion. So if you weren't sure about this, you might, now that you can see this, and now that I've said your hydrogen sulfate ion is just your negative ion, where are you going to attach it? You might be able to have a go. All right. If not, don't worry. So we've got the first step, 2 curly arrows there. It's going to go this way because that's a secondary carbocation as opposed to the positive charge being on the left-hand side. And you're going to get that, right, as your major product. Whatever that's called. Methyl, ethyl, hydrogen sulfate, doesn't really matter, okay? Your primary carbocation would have formed in that pathway, and that's comparatively less stable. You can see by this point, I've kind of got fed up of writing the same thing over and over again. Hopefully by now you get the idea. This carbocation is less stable than the one that formed the major product. Last one. Okay, so this is a branched cyclic alkene, all right, and hydrogen fluoride. Slightly wonky looking, but it follows the same logic, at least initially. And then you think about where you put your positive charge, think about the major products and minor products and stabilities of carbocations. It stands to reason that this is going to be the primary pathway, the faster reaction, because you put your plus there and your carbon's attached to 3 other carbons. It's a bit of a weird one, just because it's cyclic, but it's attached to 3 neighboring alkyl groups. So it's going to go that way if it can. And you're going to get this molecule as a result. Okay. The comparative sort of alternative pathway would have occurred via this carbocation, which is comparatively less stable. So, like I said, I actually think that's probably about 2 lessons worth of stuff because there's actually a lot to go through. The video's probably wound up being quite long, but that's all right. I don't mind because I said that in the introduction. All right. Obviously, this is something that it's easy to kind of go away and think you've learned this until it comes up again in a few weeks or a few months. You're not going to know whether you remember it well enough or not. Okay. We are going to revisit it, obviously, but we'll take a little break from electrophilic addition for the most part for the next in the lesson after next. We'll do a bit of consolidation next time. Thank you for listening.